And now we will talk about the voltammetric sensor. That is the most commonly used one. So the voltammetric sensor is an electrochemical sensor that measures the current responses of an analyte as a function of an applied voltage. So we will apply voltage and we will measure the current, but we will apply the voltage and we will also sweep the voltage, and we will fix a range from this to this of an applied voltage. And then in that voltage range, we will try to measure the current. So it is widely used for detecting and quantifying electroactive species in biological, environmental, and industrial application. So how this thing work? For this thing, we need three electrode. So the working electrode, where the analyte undergoes oxidation or reduction. The reference electrode, which will help only to maintain the stable potential, and the counter electrode that complete the circuit between the working electrode and counter electrode. Okay, and it balance the reaction. So a specific voltage is applied, as I told you, applied across the working electrode and reference electrode. And current measurement: when the analyte undergoes an electrochemical reaction, a current is generated and measured. And then the data interpretation. The resulting voltammetric curve, current versus voltage graph, provides information. Yeah, I'm going to show you those things. But before that, I will tell you how there are different kinds of voltammetric sensors. So what are the types? Maybe you have heard already: cyclic voltammetry, differential pulse voltammetry, square wave voltammetry, then the linear sweep voltammetry, and stripping voltammetry. So the most commonly used one is the cyclic voltammetry, and DPV also is we find a lot, but also you can find square wave voltammetry and linear sweep voltammetry. So if we just talk a little about the cyclic voltammetry, in this cyclic voltammetry is one of the most commonly used one electrochemical technique to study the redox reaction, electron transfer kinetics, and how does it work? Okay, so the applied potential ramps up a predefined value and then reverts back. I'm going to show you in the next experiment, of course. And for this cyclic voltammetry, for all those voltammetric sensor, we always need three different electrode: the working electrode, reference electrode, and counter electrode. And we also need a potentiostat. That's right. To measure this thing. And it has different, the cyclic voltammetry has advantages over the other. Like, it is very quick and straightforward technique. It provides qualitative and quantitative redox data, and it can analyze reaction kinetics and mechanism. But it also has some disadvantages, like it cannot provide absolute concentration without calibration. So the calibration is necessary. You always have to do that. And it requires proper choice of a scan rate and potential window. So you have to find out the scan rate at which you are going to do this cyclic voltammetry. So there is also another one is called the differential pulse voltammetry, which is an electrochemical technique. Here it applies a series of a small voltage pulse superimposed on a linearly increasing base potential while measuring the current. So unlike CV, which requires a continuous current response, DPV measures the difference in current, the delta I, before and after each pulse. It also has some advantages and disadvantages. So it is very it higher it has higher sensitivity than CV, and it better resolution it has, so allowing simultaneous detection of multiple analyte. And it has improved detection limit, but it also has some limitation, like it requires precise parameter optimization, and yeah, it has lots of parameter than the CV, and it can be affected by electrode surface fouling and longer analysis time compared to some other technique. So it requires little more time. Another common one is the square wave voltammetry. So the square wave voltammetry, it how does it work? A square wave potential pulse is superimposed on a linearly increasing staircase potential while measuring the resulting current. So the current is measured twice per circle here, once at the forward pulse and once at the reverse pulse, and the difference recorded. And also, it of course it reduces the background noise. So like the DPV, the SWV, the square voltammetry, it also has higher sensitivity and very faster scanning, low background noise. Yeah, it is faster scanning that than DPV, and it has very less background noise, but it requires precise optimization. That is the most challenging part, and more complex data interpretation also. And we can talk about little about the linear sweep voltammetry. That is actually a linearly increasing potential is applied here to a working electrode while measuring the resulting current response. So it's a linear, it's not going and coming back type. So the scan is performed in a single direction, either anodic or cathodic, without reversing the potential. So how does it help? It is basically simpler than CV, but it cannot provide full reversible information unlike CV. So it has limited to single directional redox analysis. So I'm going to show you the paper that I have completed in my PhD, and I used linear sweep volumetry here. Okay, so let's talk about this paper. So in this one, the title of the paper is Flexible Screen Printed Electrochemical Sensors Functionalized with Electrode Deposited Copper for Nitrate Detection in Water. So that's a flexible sensor, we are calling it, because we prepared the sensor, screen printed sensor on top of the PET sheet, and we electrode deposited copper on top of the working electrode, and we're calling it for nitrate detection in water. So here is the real image of the sensor, and we are measuring the nitrate. So the nitrate is going to reduce to nitrite when it is when the copper is present. So the copper is catalytic, doing the catalytic reaction here. So in this figure, it shows the fabrication process. You can see the detection and also the detection mechanism of the proposed of this nitrate sensor. And very briefly, you can see here the psilocybin chloride ink were screen printed here on top of the reference electrode, and both the working electrode and counter electrode, we use the silver ink for screen printing on top of the PET substrate. And here you can see the reaction to reaction. Okay, I'm at first discussing these two curves. So to evaluate the analytical performance of this sensor, the linear sweep voltammetry was applied Okay, so the calibration curve here. Okay, before calibration curve, we can see here the what are the potential range we are taking here from minus 0.1 to minus 1.4, and in this range of potential range, we are getting different reduction reaction. So there is one reduction reaction, second, third, fourth, right? So the first two reduction reaction is coming from copper oxide and cupric oxide, and then this reduction reaction is coming from the nitrate, because nitrate is going to be nitrite here, and further this nitrite is going to be ammonia here. These are the two reactions. So if we already know that in this reduction reaction, the nitrate is going to be nitrite. So when we're going to taking the current, we're getting here this current versus the different nitrate concentration starting from 0 and then 0.1 till 5 millimole. Then we're getting a nice calibration curve, and from the calibration curve we're getting the calibration equation. So this is how the sensor will work. So I think you get an idea about how this voltammetric sensor is working using the CV. So now we will talk about another one where the last one we use LSV. In this one we will use cyclic voltammetry. But before that, let's go to the title. The title is an APTA sensor based on a flexible screen printed silver electrode. Okay, so here is the silver electrode, the same kind of electrode. But now we will design the working electrode in a different way. We will functionalize the working electrode using different mechanism. So, and for the detection of chlorpyrifos, it is the most commonly used pesticide in agriculture sector in US and also in other countries. So we have to detect this pesticide in food or in water with the help of this voltammetric sensor. So how does it work? At first, here you see in the working electrode, we are using 11 MUA, one kind of chemical, and then EDC NHS chemistry, and then we're using aptamer. Aptamer is a kind of DNA. So we're using this kind of DNA aptamer here on top of this EDC NHS chemistry, and then we when and this aptamer is very specific to chlorpyrifos. Because we developed this aptamer, we ordered this aptamer from a company, and we told them that it has to be specific to chlorpyrifos. So when there is the chlorpyrifos in water or in soil or in the food, and we use this sensor, it attach this chlorpyrifos with this aptamer, and this is how this sensor is working. So here is the mechanism of the sensor. You can see here. Uh, in this figure, you can see this figure illustrates the working principle of aptamer. APTA sensor, we're calling it APTA sensor because we're using this sensor. So this is one kind of biosensor, but we are specifically calling it APTA sensor. So in the absence, you can see here, and there is the absence of CPF, there is a chlorpyrifos, and there is the presence of CPF. When there is the absence of CPF, we are getting higher oxidation current, reduction current in this cyclic voltammetry. And with the presence of CPF, we are getting less current. So that is how this sensor is working. That means in this the aptamer we are using here, that created a barrier toward the electron transfer. So in this sensor is working in opposite way. So when you are increasing the concentration of the CPF, we are getting lower current, because here the aptamer is attaching with this with the CPF, with the chlorpyrifos, and when we are increasing the concentration of CPF, there is the more the barrier is coming. So we are getting less and less current. So yeah, and here is the analytical performance of this sensor. And here you can see the range, the detection range for this sensor is starting from 1 nanogram per ml till 10 to the power 5 nanogram per milliliter. And from this figure, you can see the more the amount of CPF is captured by this working electrode, working surface of the sensor, and the higher the number of aptamers that undergoes the conformational changes. That means it's bending closer to the surface of the working electrode, so thereby increasing the electron transfer resistance. So this relationship between the reduction peak current and the logarithm, we got the logarithmic value. Yeah, the logarithm of the target concentration is plotted in this figure. And a strong linear relationship can be seen here. The R squared is 0.99. That means the sensor worked very nicely. Okay, so here in this, the previous one, you can see the LSV is helping for this sensor calibration. And in this one, we're using CV. And the next one, yeah, in the next one, we are also using CV. So here, this is the last example of the voltammetric sensor. Here we're doing what we're using. Yeah, let's start with the title at first. Processable and nanofibrous polyaniline polystyrene sulfonate. Shortly, we call it PANI PSS, polyaniline PSS. Okay, PANI PSS for the fabrication of catalyst-free ammonium sensor and enzyme-coupled urea biosensor. So here two things we are detecting, but I'm just showing you the ammonium sensor part. So the ammonium sensor, how they are preparing the sensor using the PANI PSS, and then they're using the cyclic voltammetry. So here what is happening, and at first we can talk about this part. So the PSS and the PANI, right? And the PSS here, it provides a soft template or nanofiber formation, and it enables the detection of ammonium based on an intrinsic doping dedoping mechanism. Here you can see doping and dedoping. And the PANI polyaniline, it has a unique selectivity for ammonia via this reversible doping dedoping mechanism through the interaction between the lone pair electron on the nitrogen atom of polyaniline and ammonia. So here initially what is happening, the nanopani, when it is positively charged, then yeah, when it is positively charged, then the PSS is negatively charged. So they serve as a non-mobile polyanionic charge compensator within the polymer matrix. So in the negative scan of the CV, in the negative part, so from here, 0 in this part is positive, we are also going negative. Negative scan of the CV, the positively charged PANI backbone in PANI PSS matrix is reduced to a neutral state without a charge. And while the positively charged in this part, this ammonium molecule insert into the nanopani matrix, which you can see in this equation. So in the nanopani PSS, and there is the ammonium ion, and there is, you need one electron also. So then the ammonium ion insert into the nanopani PSS matrix. So that is happening in the dedoping state. So when we are running the cyclic voltammetry, it is constantly happening, dedoping and then doping. So it is taking the ammonium and also removing the ammonium. And this is how this sensor is working. So it can be seen from this figure, doping, dedoping, and the detection range here from 0.5 millimole till 8 millimole. So I'm not showing here the calibration equation, but from this sensor you can see when we're increasing the concentration of ammonium, the oxidation part is also increasing, the reduction current is also oxidation and reduction, both current is increasing, and that is also increasing in the dedoping and doping state. So beside this calibration thing, also this one is measured for the sensor is measured for selectivity test. The selectivity test, yeah, I think this one is DPP. So differential pulse voltammetry is applied for detecting this. You can see the all the things that they're using CV and then DPP. DPP is using for the selectivity test. So the selectivity of the nanopani PSS was studied for the detection of ammonium in a normal urine model. Here it contains how much? 200 micromole of ammonium, 20 micromole of creatine. Yeah, different concentration, and they are checking if how the sensor is working. So and this, so the figure, it shows the nanopani PSS sensor had a relatively high signal response for the red dotted one, this one for ammonium, while the signal response from other interfering molecule were similar to the blank, like this one. And when the signal response obtained by the nanopani PSS electrode for ammonium was normalized to 100%, the signal response from urea or the other things are really less percent. In percentage, these are really less. And the result demonstrate for the fibrous nanopani PSS interfaces can be used for the selective detection of ammonium.